What's up, guys? It's me again, Sir Ernest, and today we will discuss a sample problem related to the Lagrangian Dynamics. So the problem reads, find the differential equations of motion for an elastic pendulum. So when you say an elastic pendulum, that means a particle of mass m is attached to an elastic string of stiffness or spring constant k and an stretched length of L naught. Assume that the motion takes place in the vertical plane. Okay, so how does this look like? Now, so first, just like a simple pendulum, it should have a support here. Okay, so if this is the vertical axis, okay, so instead of a simple pendulum with a length that is a constant, or we have with a constant length, the particle with mass m is attached to a spring of stiffness k. Okay, and at this point, this is at its relaxed state or relaxed length. Okay, now if this starts to move because of gravity and everything, this will start to move. This will oscillate along this direction while this particle is swinging. So it will be some sort of a chaotic motion. And what is now the equation that will determine the position of this particle at any given time? Okay, so let's say at a stretch state, so let's say somewhere here, so this is your mass m, so your spring would be stretched like this. Okay, so at this moment we call this r. Okay, so this is your instantaneous length of the string, and that includes the relaxed length or unstretched length L naught and some elongation, or you can also do this by compression. So if this is for compression, this will still be plus x, but the value of x will be negative, where x is the amount of stretching or compression of this spring. So in this case, this is x. Okay, so at this point, you can also determine our h or y if you want. Okay, now this is now our figure. So now we can now determine the Lagrangian by knowing the kinetic energy. So just like in a simple pendulum, we can express the motion of this particle in polar coordinate system defined by this direction. It's called that r and theta. So in polar coordinates, the kinetic energy T is equal to 1/2 mv squared, where in polar coordinates, as we already know before, that in polar coordinates, the speed, square of the speed would be r dot squared, and then you add it with r squared theta dot squared. So you will notice that kinetic energy is a function of r dot, and theta dot. So at least the Lagrangian will be a function of r, theta dot, r dot, and theta dot. Now the potential energy, on the other hand, is just equal to mgh because of the presence of gravity, but because the string or the spring, it contains elastic potential energy, so we have to include that as well. So the total potential energy will be mgh plus 1/2 kx squared. Okay, so from our definitions earlier, mgh, or h, would be negative r cosine theta. Okay, so this is negative mgr cosine theta. And then plus 1/2 k times x, which is r minus L naught, right? Okay? So that's r minus L naught and square. Okay? You follow? Okay, so therefore, the Lagrangian of the system will be this minus this. So this is 1/2 m r dot squared plus r squared theta dot squared plus mgr cosine theta minus 1/2 k times r minus L naught squared. So you notice that L, or Lagrangian, is a function of r dot, theta, and theta dot. So this suggests that we have 2 degrees of freedom. So therefore, we have 2 Euler-Lagrange equation. Now, using the Euler-Lagrange equation for r, so for r, the Euler-Lagrange equation will be partial derivative of L with respect to r, and this is equal to total derivative with respect to time of the partial derivative of L with respect to r dot. Okay, so this term will be m r theta dot squared coming from this term, from this term. Okay, then plus coming from this term. So this is plus mg cosine theta. Okay, and then minus coming from this term, which is k times r minus L naught. So this is 2k times 1/2, so that's k times this term times the derivative of this term with respect to r, which is 1. Now this is equal to total derivative with respect to time of mr dot, which is mr double dot. So therefore, r double dot acceleration term will be equal to r times theta dot squared plus g cosine theta minus k over m r minus L naught. So this is your equation of motion in r. Okay, so now let's look at the equation of motion in theta. So again, we have derivative of L with respect to theta equals the derivative with respect to time of partial derivative of L with respect to theta dot. Okay? Okay, so let me just put in a paper here. Okay, now let's do this. So this term will be equal to, so we differentiate this with respect to theta. So this is negative mg r sine theta, right? Right. So this is now equal to the total derivative with respect to time of partial derivative with respect to theta dot, this one. Okay, so this is m r squared theta dot. Okay, now m is constant, right? Okay, so we can cancel m, but we can do that later. So this term So can be written as m times the total derivative of r squared theta dot. Remember that r and theta dot are both functions of time, so we use product rule, then chain rule. Okay, so first copy the first, so that's r squared, then the derivative of theta dot with respect to time, so that's theta double dot, then plus 2r r dot theta dot, so that's chain rule. Okay, so from here there are two common factors. Number one, m, so m is cancelled with m here, and then there's a common r here, here, and here. So therefore we can now rewrite this as negative g sine theta equals r theta dot, theta double dot, plus 2r dot theta dot. So finally, the equation of motion would be theta double dot equals negative g over r sine theta minus 2r dot theta dot over r. So this is the equation of motion for component theta. Okay, so we have two equations of motion, one in r and one in theta. Now please take note that you don't have to, well, it's preferred to write the equation of motion like this: acceleration equals an expression, acceleration equals an expression. But we can actually settle with this expression. This is fine with me. This term, or this expression, or this equation is actually the same as this equation. So I have no problem if you express your answers in this equation or in this form. Okay, but I prefer this form. It's easier to see. Okay, so that's it. This is the equation of motion for an elastic pendulum. Okay, so thank you for watching. I hope you learned something today, and I will see you again in the next video. Bye bye.